Hey there, how you doing? Welcome back to the channel. So today what we're going to do is we are going to look at this is the second one in the video on the clock project. So basically what just really quickly, I was doing a project here where I was going to make a clock. The idea behind this clock is that it was going to be able to have multiple digits where you could do hours, minutes, and seconds like normal clock, but also set long-term countdowns of years, months, and days. And so the idea behind it is I'm going to have basically like a little microcontroller that's going to have a real-time clock calendar in it, and that's going to help do all this stuff. And so basically, here's the displays. Now, what I've done is I've gone out and I've gotten IV11 VFD tubes. So they're a little smaller than IFV12s, but they're a little more reasonable cost. And so now I have one of those. So this is kind of what I'm looking at. So let's do this. I think you should be seeing this screen. So what we have here is I have this little circuit set up. And what I'm doing is I have a single tube set up, and I have this little battery here is the little battery there, a AA is providing 1.5 volts across the pin 1 at 11. So that's the cathode, and that's the grid voltage. Now, if you look at that, like what I'm seeing, and I don't know if I'm going to see this in the video, you see these two horizontal lines. Those are actually the grid voltages. That's the 1.5 volts. Now, what I've done is I also have connected to 9 volts to the grid. And so careful. The 1.5 is across the heater. There's a heater element there. Okay, and so that's what that's powering what's called the basically the cathode or whatever, the heater. And you can see those two little bright lines. That's what those are. And then we have the grid. Now what I've done is I've connected the grid, and I've connected this whole plane here to a 9-volt battery probably right here. And so what this is going to do when I flash it, whatever I've connected to the 9-volt battery, including the grid, is going to light. So I have it connected up to these two segments right here. And you can see that, it's lighting up these two segments. So now, so basically, that's what's going on there. That looks reasonable. So what I was trying to do, turn on the, see how it looks with the light on. I know I turned the light low. Yeah, it's hard to see. The camera's not really catching it very well, but I need to work on that. But one of the things I was working on was trying to make a 1.5 volt supply. So I have this little circuit here, which is an LM, basically an LM317 circuit. And unfortunately, this circuit is not, it's basically smoking that resistor. I don't know if you can see that resistor there. But this one here, that's black. It shouldn't be that way. It's burning. And so I don't know what is going on with it. I've checked the schematic several times, but it's just not working. So what happened was that circuit, that 1.5 volt circuit, ended up burning out this tube. So if you look in this tube, you can see that, yeah, see that black stuff in there? Yeah, that's not right. That's all burnt out. So something went wrong with that circuit. I don't know what. I suspect that, I was trying to apply 1.5 volts across the heater, and I suspect that I was applying the full like 27 volts somehow. So I still don't know what's going on with that. But yeah, so, and then the other thing I have here is I have this PIC microcontroller board. So what this guy is doing here is we have a USB, and we connect to the board. And then what we can do is we can connect various pins, port pins, to basically drive our logic. And this will connect through a little USB cable here. So there's a couple things here that I sort of realized. So let me show, oh yeah, let me show this. One of the problems is I was messing around with this. And first of all, I was like, there's several issues here. One issue, I'm just going to take the battery out for now. And we're going to take the battery out, the 1.5 volts. And let's see, is that? I think you can see the little, the two horizontal lines are gone. So because I put the voltage off that. But one of the things that I was doing is, and I was basically I have headers here, and I basically have these different ports. There's 3 different ports in there, port A, B, and C, all 8-bit general purpose IO that I can use to drive. And the plan is to take these and drive, my chips out here. But the thing is, and this is what I realized, and then I realized like, oh no, I need to go buy some more chips because I realized there's a problem with that. So let me explain what the problem is with that. So can you see this? Okay. Yeah. So what's happening is we have to understand that we have we have a computer and we have a USB cable, and we have this little board. So this is going to be our microcontroller board, right? That's the one in red over there. So what's going to happen is, I have these, VFDs and all this stuff that require like 25 to 30 volts, 1.5 volts, and then I have all this logic, which is going to be 5-volt logic, etc. So what's going to happen is I can't, like, I was doing an experiment and I was powering some of these chips from this logic over here, the 5-volt supply over here, which you can do a little bit, but you have to be careful. This board is not going to supply significant current. And I'm using like a lot of potential chips that are going to draw a lot of current. So, but then I realized there's another problem here. If you look at my circuit here, this is connected to the actual, like, for what the idea is that I'm going to use an actual wall wart, and that is basically going to be 12 volts coming in. Now, what happens is it is DC, it's 12 volts, it's isolated, but it is, it's coming from a separate source than the computer. So it comes in this regulator, comes in at 12 volts, and then gets boosted up to 25 volts. And then the 25 volts is going to run all my regulators here that I'm going to need for the Nixie, right? Now, the thing that's going to happen is I realize that there's a risk here because this voltage here is 12 volts, and the voltage on the output side of this is 1.5. I'm sorry, no, this voltage is actually higher. This is 27 volts because I'm making it with this regulator here, right? So I'm using this boost up regulator. And so the point is I have 27 volts here, and the point is one side is we consider it ground, right? And then this is going to be ground common to any other power supplies I create. This is LM317T. And I need to create like 5-volt power, 1.5 volt power. And then this boost regulator here is creating the 25 volt power. And so I need all these voltages that I can't get from this little board over here, right? I can't get it from this board. Now, what I realize is when you go and you go to connect these boards up, quickly, like you have a ground over here on this board, and you can connect ground to here. But the thing is, at some point, I have to connect this ground to this ground over here. And if you look at it from a big picture, taking this ground, which is coming from a USB 5-volt supply coming from the computer, to run some chips here, and then having these chips control this circuit here, and then having to connect it to the same ground here, this comes from an entirely different circuit. This is an entirely different thing. It's a totally different power supply. So the thing is, it might work, but it's really dangerous because you got to understand that like the common point ground over here for this board is there's not much of a guarantee that it's going to be at the same ground point as this point over here. And so if I go to connect those off, you could have all kinds of ground currents running and all that stuff. So what I realize is that I need something extra in this. So if I go forward and I say, well, okay, I'm going to get rid of the USB and I'm going to get rid of that, for example, because I can program this, flash program this chip with the program I want to run. And that's one possibility. But I think for the time being, I'm going to want to be able to connect it to the computer. And I may want to do that going forward, but I don't know. But the problem is I'm creating all these voltages that I have to get from another supply. And then if I'm connecting USB, I'm getting that supply. So what really happens is you have to kind of consider, like here you have the microcontroller board running off the computer's USB, and this control now is going to chips in the Nixies, the VFDs, off a totally different supply coming off the wall board. So what you really have to do is you have to isolate these because these chips, ground is not ground. The ground here may not be the same ground as over here. And this is something that can happen where you're like, this is why they create these things called optocouplers. And the purpose of optocouplers is a way to send a signal across without having to send over the power with it, right? Because it's going to be isolated. So what I realize is for these control signals, I'm going to need optocouplers to make sure that the power supply in this microcontroller board in the PC is not interfering with the power supply for this logic over here. So to do it, I have to have totally separate supplies. And then the control signals, we transfer them optically, and that's how we're going to isolate it. I think this is really a safe thing to do. And I've seen this in other schematics. I saw it in one schematic for there was basically like a kind of an EEG thing, and they had it connected to the computer, and they like did a lot of work to make sure, because if you have a fault, think about it. If you have a fault, I mean, you know, this is your computer over here. This thing's got 120 in it, you know, and then over here, this wall wart is got, you know, 120, and then it's isolated, but you know, with a wall wart transformer, that's fine. But still, you know, you have this potential where it's like, you just can't take what you're calling ground here and just randomly connect it to what you're calling ground over here. You know, so you can't just randomly connect ground in this stuff over here to ground over here. They're not the same. Ground isn't a magical thing. It's just a common point. And these are so disassociated from them, you have the possibility of current running between the grounds. That's really what it is. So because of that, you know, we're going to have to go with optocouplers. So I need to go get some more chips. So there's a couple things. So first of all, I need to figure out why this stupid regulator circuit is not working. When I had looked at it, it was producing, this is trying to generate 1.5 volts. It was doing it, but I don't understand why it's not. So let me look at that here. What I'm going to do is share screen. Share this one. So yeah, here's what I copied the yeah, so here's the circuit that I'm trying to use. So I'm trying to create a 1.5 volt supply here. So I'm using this circuit, so I don't know what the problem is. There's a couple things here. So basically, you know, you have this calculation you can do to calculate your voltage output based on R2 and R1. And then over here, they kind of go through this equation to say, hey, your R1 should be, you know, 120 to 240 ohms, something like that. So what I did is I picked R1 equals 220. And then I'm going to pick the R2 to get me the voltage out that I want. So in the spreadsheet here, I can just put this equation into the spreadsheet. So that's what we do. And then what we have is I've adjusted and found a reasonable existing R2 that I have to make 1.5 volts. And then I also planned for the 5 volt supply, and I need 660 ohms for that. Both of these are standard resistors that you have. Now, the next thing that you have to do, you know, you do have to be careful. You have to be like, you know, how much power is going to be dissipated in these resistors. And hence, I'm looking at this really big because I have a resistor over here that is has basically melted. It's literally melting. So, you know, we have to check that. So the IREF, we have the equation here is the IREF. So basically, the current going through the resistors, remember the same current is going to go through both resistors. This is 100 microamps into port A. Port A it's supposedly set to always do 100 microamps. So there's transistors, all that stuff in there, and it's basically very high impedance. So there's very little loading. So you can just have V out going over R1 in series with R2. So you basically take V out, which in this case is 1.5 volts, see in the blue, and over the sum of R1 and R2. And then that's going to give you IREF, what I call the current going through the reference resistor. Now it's going through both resistors, right? Because you only have 100 microamps here, very tiny, just ignore it, right? And so what you have is you have an IREF of 5.6 milliamps. Now, to get the power on these resistors, what you do is you take the value of the resistor. It's basically I squared R. So we take the resistance value times the current going through it squared. So current times current. So when we do this, we get 7 milliwatts, right? Okay, so we have 7 milliwatts there, and then 1.5 milliwatts there. 7 milliwatts here and 21 milliwatts there. So now the question is, well, what size resistors do you need? So I have over here, okay, the ones I have are 1/4 watt, 0.24. So the 1/4 watt resistors, and so that's 0.25 of a watt, which is 250 milliwatts, right? So these resistors that I have should be plenty strong enough, plenty capable of dissipating 7 and 21 milliwatts. You know, normally like with like power on a resistor, you want a 10x factor, 2x, 10x, something very large, because usually it's very small amounts. So we should have that covered. So basically right now, as I don't know what's going on with this circuit, it's kind of inhibiting me a little bit, but I don't know if there's kind of a problem going on with it, the way I'm feeding it. So that's something I have to look into. Hey there, welcome back. So okay. So yeah, so the basic idea is going to be, I hope there's not too much work involved, but there may be a little more. May need a resistor here, transistor there. So that would kind of stink if I have to add that stuff. But basically, the idea is that, wow, why is there so many? Let me see. It's funny how there's so many little connectors on that guy. Let's go. Opto, okay. 6, make it small. Okay. Okay, so yeah, the idea is that what we're going to do is just going to stick little optocouplers in here between all these guys. And unfortunately, what I'm looking at, I need to look at the circuit more, but apparently I'm going to need some resistors and stuff to make that all work. But basically, it'll look like this. You'll just have an optocoupler. So anything going out to our drivers, so the grid control, the shift data, we'll have one, and the, let me send this guy to the back. All right, so, okay, so everything to the left here is going to be basically, you know, the PC/USB power domain. And on this side, and then on this side, it's all going to be the, basically the VFD power supply domain. And so what's going to happen is in our VFD power supply domain, what is going on is that, as I pointed out, basically in this domain on the right, we're going to have a separate power supply where we're going to generate all the different varied voltages that we need. On the left side, all the voltages are just going to be driven by the PC. Now, that might change because if I don't connect to the PC, that's a really good question. If I don't connect to the PC, then I don't have a power supply. See, then I need, like, there's a barrel jack on this and I need to provide power. So I may need to have, that's interesting. I may need to have a switch or a jumper or an option to basically provide power from my power supply over here. Interesting. So I may need to do that. So basically what would happen is if you plug in, let's see, if you plug in the USB, then USB would power it. But if you don't plug it in, then you get your power from somewhere else. Ooh, I have to be careful how I do that. Like, do I want to put some kind of automatic switch to do that? Very interesting. Not sure what to do with that. Well, I think that's it on this one. So basically we did get the I'm sorry, not Nixie, the VFD tube. We're able to get it to light. We're stuck with some problems with the voltage supplies. My voltage regulators are messed up right now. So I got to work on those. And then once I can get the voltages working, then we can kind of get like one tube driving I definitely, I need the, so basically, certainly for the development side, I need to just have the PC connected to the board, load the program, experiment with it, get it running the way I want. So I just need to be able to do this. So I really need these opto isolators in there to prevent there from being any kind of issues with the power supplies corrupting. It's funny because you mess with stuff in with guitar and stuff, and yeah, you get yourself like ground loops, all kinds of stuff going on, and so it's very interesting because in reality, when you look at it, you say, oh, there's 5-volt supply on the USB. Well, there is, yeah, sure, but it's not. It doesn't necessarily. Does it really have to be 0 to 5 volts? I mean, is there really anything stopping it from being plus 10 to plus 15? So that's kind of where the issue becomes. I mean, probably not. They wouldn't really do it that way, but the problem is there's how do they do it since USB is connecting between computers? Yeah, that's a good question. They may have to do isolation in there and stuff. I don't know what they do. It's really interesting. Yeah. Okay, well, that's it for this one. So yeah, so we're going to have to add some opto isolators in there and get things going. Talk to you later. Bye.